All right, I think we'll go ahead and get started. It's 2 o'clock now. My name is Tate York. I am an image analyst at NeuroScience Associates, and I want to thank you for taking time out of your busy schedule to join us for this webinar today. So what we're going to talk about today is a little bit about our imaging and analysis services. And this is just a brief overview of what we're going to be discussing today. I'll talk about our imaging capabilities and services, go over some of the equipment we have in-house, and then I'll go into a little bit more detail about the image analyses that we offer, including particle analysis, densitometry, volumetric calculations, and we'll finish up with a really fun topic that we've been enjoying a bit recently with 3D tissue reconstruction. So I'll go over a little bit of the processing steps and show you some examples of a pig brain and grizzly bear brain that we've reconstructed in recent months. So this is the equipment that we have in-house. I'm not going to bore you guys with all of the technical terms here. We have 3 Nikon scopes. One is fitted with a fluorescence module, and we have different filters showing a range from blue to red fluorescence, all equipped with digital cameras. And we actually have a slide scanning system fitted with a focus motor wheel from Prior Scientific. And the system itself, the software for image acquisition and the glide stage is actually put together from a company called Objective Imaging. So with all of this equipment, we're able to provide bright field whole tissue scans at 10 and 20x using our scanning system from Objective Imaging. We also have manual scopes that we can take more specific images of your tissue in bright field and fluorescence. We have objective lenses ranging from 2x all the way up to 60x, which is our oil immersion lens. Let's see. And we also offer block face imaging during the tissue sectioning process. And we'll hit on this more a little bit later when we get into the 3D reconstructions and that processing. So what we offer with this equipment and all these capabilities is whole tissue scans using our scanning system, digital capturing of more specific regions of interest at higher magnification. And so these images will send to you either through an FTP download or an external flash drive or hard drive. And all of these images will keep stored at our facility just in case something happens with a shipment or a download, if something is damaged in transit. So we've got some sample images on our website that I'm going to show you. And if you've already visited our website, please be sure to go back and look at these again if you haven't already. It's under the imaging website, or under the imaging tab under services, imaging, digital imaging. So this is just a slideshow showing some of our images that we've scanned recently and over the past few years, some with our scanning system and some with our manual scopes. Now, when you're wanting to consider doing analysis on your stained tissue, there are a few criteria that you should consider before deciding on what type of analysis you're going to need. And one of the most important things to consider is what is your region of interest, or maybe you have multiple regions of interest. So having a defined area of what you're looking at is going to be very important when it comes time to delineating an area of interest for the analysis, so that you're able to, and so that you're able to view it yourself, and so that we're able to perform the analysis for you. Another important factor is, what's your endpoint? For your specific study, what do you need to know? What kind of information do you need from the stained tissue? Are you looking at number of cells? Are you looking at an area of positive staining in the tissue? Maybe you're interested in more of volumetric calculations. So two very important things to consider. On top of this, what stains are appropriate for achieving this endpoint? If you're looking at astrocytes, maybe you want to consider a GFAP or Nestin stain for microglia and IBA1 stain, or maybe there's a specific antibody that you have in-house, or that you need to look at an even more specific region or object. In addition to this, there are varying degrees of analysis depending on what your study needs. So if you're doing a preliminary study and your analysis needs don't need to be incredibly detailed, if you're looking for large differences between groups, let's say, then maybe you're not looking to spend a whole lot of money on analysis. And that's where the question of, for example, image analysis or stereology comes in. So stereology is very good at many types of analysis, volumetric calculations, cell quantification. But on the other hand, it's also very time consuming and very expensive. So what we can offer at NeuroScience Associates is an image analysis alternative that can get you good quantitative data without spending all of the time and money for doing stereology. Granted, stereology is needed for some instances. Say you're counting Th positive cells in substantia nigra. Image analysis isn't really going to do the trick for that, because the cell population is so dense in that area. You need something along the lines of stereology to get good numbers for that. And again, whenever you're considering this, you need to know what your region of interest is. So if you call someone up and say, hey, I want to count all of the cells in the brain using a Nissl stain, and I want to use stereology, they'll probably give you a weird look and tell you that it's going to take a really long time and a lot of money. So being able to fine-tune your study to what you need within a region of interest is really going to help accelerate the image analysis process. Another example is more or less accurate volumetric calculations. There are different methods for doing this, and it ranges from a less accurate method of calculating volumes to more accurate methods. And as I mentioned before, if you're doing a preliminary study and you don't need exact volumes, if you're just trying to show a difference, and you're trying to, if it's a proof of concept or something like that, then maybe you don't need the really detailed volumetric calculations. So another criteria to keep in mind is we don't always know what analysis type is needed until we actually see the stained tissue. So once the tissue is stained and mounted on the slides, then we'll get it under the scope, take a look at it and say, this looks like a good candidate for densitometry or particle analysis, volumetric calculations, and really, if there's good signal to noise and positive staining versus the background versus the tissue, that unstained tissue, then you're really increasing your chances of a good analysis pipeline. So let's move into some of these types of analyses. The first one we're going to talk about is particle analysis. So what is this used for? And I'll go back again, it's used for cell quantification to a degree. Like I mentioned before, stereology can be better depending on what the study endpoint is, what objects you're counting, and what the staining looks like. So if, like I said before, if you have a TH staining in substantia nigra, you're really going to want to go the route of stereology. There's really no other way to count those cells other than stereology. But in an example that I'm going to show you here in just a minute, image analysis really has come a long way, and we've developed a few tips and tricks to get good quantitative data out of certain stains. And the first example I'm going to show you is a double stain showing nu-in positive cells and degenerating neurons stained with the aminocupric silver degeneration stain. And we're going to look at cingulate cortex in a rat coronal section. So all of the analysis that we do here is mainly through Fiji. And it's a great resource. It's an open source software platform. And once you get the hang of it, it's really an invaluable resource. There's a large community online throughout the world that are constantly making new plugins, updating the software. So it's really a handy tool when it comes to analysis. So what we have here is an image of cingulate cortex, and you can see in this image the different populations of cells. So the black cells are the degenerating neurons stained with the aminocupric silver degeneration stain versus the brown tan tincture of the nu-in positively labeled cells. And so what we wanted to do is take a region of interest in cingulate cortex and determine how many degenerating neurons there were compared to the number of nu-in labeled cells. And so there is quite a few processing steps to get where we needed to be. So this just shows the region of interest traced out with this red line. So what this is a binary image of the degenerating neurons. So after thresholding, filters were applied, and this one I believe doesn't have the watershed filter applied. And what that is it's a filter that separates close proximity neurons that are touching. It'll go in and separate those that are touching based on the parameters that you input into the filter. So what we can do with this binary image is run a particle analysis. And this is another tool offered in Fiji, and you can change the parameters, whether it's by particle size or circularity of the object. And so what we can do for better visualization is create an overlay over these degenerating neurons compared to the nu-in positive neurons here. And we do the same thing, and see here the watershed filter is applied to these new and positive neurons. It's segmenting the close proximity neurons with this filter, so you get a more accurate count in the end. And so we also throw an overlay on top of that as well for visualization. And this is just a combined image showing both overlays in the region of interest. And so what this provides is a ratio of degenerating neurons versus new and labeled neurons in this region of interest. So you can quantify both sets of populations and compare these to one another. So you're getting a ratio in the end. Looks like it started all over for me again. Let's see. Okay, so the next example I want to show you is along the same lines, but it's a little bit more specific. It's looking at Alzheimer's disease plaque loads. And for this specific example, we'll be looking at a mouse sagittal cortex. So what this analysis is going to give you is the number of plaques in a given region of interest. You can determine the area of each plaque, and you can also determine a size class distribution from very small plaques to large plaques. So here's the original image. Again, this is mouse cortex stained with amyloid beta 1 to 42, I believe. So we've got the original image. Now, this is the final image that we're trying to get to. So how do we get there? First of all, we need to switch this to a grayscale image. And then after that, we apply a false color lookup table image to the grayscale image. And what you can see is based on those grayscale values, it's going to apply a color to it. And there's a variety of lookup tables. This happens to be the rainbow RGB, but there's quite a few available in Fiji. So what this does, like I said, is it applies based on the grayscale value a color to each pixel in the image. So as you can see, it's quite clearly delineating the plaques from the rest of the tissue. And what you can also see is that there's a kind of a halo of a less intense staining around this plaque core. So what you can do with this is either count each plaque, determine the area for each plaque as a whole, or you can go a step further and separate it by staining intensity, which is shown here by the yellow line circling the core of the plaque, and the blue line circling that kind of less intense halo around the entire plaque. And you can also see there's lots of tiny little outlines here. And what you can do is change the parameters in the particle analysis to get rid of those if you're not interested in those. And so you'll just be counting these larger plaques here. So the next stop on the analysis train is densitometry. And I've got some examples at the bottom here showing a GFAP stained spinal cord section. And what this is used for is to measure the amount of positive staining in a given region of interest. So as you can see here, we applied the same type of method that was applied with the particle analysis, except instead of counting objects, we're measuring the entire area of the positive staining. And this is going to be recorded either as area in millimeters squared or as a percent area of the region of interest. And again, you can break down the total area of staining by intensity. So the green in this image represents all of the GFAP staining, while the red is representative of the more intense staining. So you can get a readout on both of those intensities. Now, volumetric calculations, there, like I mentioned before, there are a few different methods that come into play with this type of analysis, depending on budgetary constraints and what you need for your particular study. So the three methods that we use are the ellipsoid method, Simpson's rule, and a fairly new plugin offered through Fiji is voxel counter. So the ellipsoid method, and there's an image on the next slide that'll illustrate it a little bit better than maybe I can say here. But it's used to measure regions of interest that are roughly ellipsoid in shape. So the irregular regions of interest are not going to be compatible with this method. But it's useful for, say, striatum or some lesions, ischemic lesions are, those are some good examples and measurements that we've made before in tissue. And so what it centers on are measurements of the height, length, and width of the region of interest. So there are very minimal measurements that are needed to determine the volume. And these measurements are used in a formula, a very simple formula. And once you plug in the values, then you can get your volume of that region of interest. So for more complicated regions of interest, we use either the Simpson's rule method or the voxel counter method. The Simpson's rule method is a formula used to define or for approximating definite integrals. So you'll need at least 11 sections for this. And it's very accurate volume calculation method. So what you would do is measure the area of a given region of interest across several levels, and then you would compile this into the formula, and we have an Excel spreadsheet that we compile everything into, and it does all the calculations, and we get a volume at the end once all of the area measurements are input. Now, another method that's pretty neat and one I like quite a bit, and I've used just recently here, is the voxel counter method, and I'm going to show an example for you here in a minute. So it's also used to determine accurate volume calculations on really weirdly shaped regions of interest. If you're trying to determine a whole brain volume or the volume of a structure like colostrum, it's you can't use the ellipsoid method. You can still use Simpson's rule method, but this method is also available. So what you would do is upload your or what we would do is upload the scale from the image into Fiji, and based on that we can determine a voxel size, so the X, Y, and Z dimensions of each pixel based on that scale. And so what it does is it takes a binary stack and it measures every single voxel in the stack for that region of interest, and at the end it gives a volume readout. So I'll go ahead and show you an example of this. So what this is a gray kangaroo set of sections that I've already changed into a binary format. The stack has been aligned, thresholded, and binarized, so it is ready for the voxel counter. And this process does not take very long at all. If you blink, you might actually miss the processing. So I'll go ahead and start it up. So it works really fast. And so here's your output over here. So it's counting in every single slice of this stack, it's counting the area. And so what we end up with is a whole brain volume of this gray kangaroo brain, which is a little over 12,000 millimeters cubed. And this can be applied to whole brain volumes, any region of interest that you may be interested in. So this is the image I mentioned earlier that shows the ellipsoid method, kind of a breakdown of what's being measured to give you your volume approximation. So this is just a general ellipsoid shape, a region of interest. And so you're taking measurements A, B, and C and putting those into a formula, and it's going to give you your region of interest. And on the bottom here, kind of shows the processing, an abbreviated set of processing steps for volume calculation with the other two methods. So this yellow outline over here is something that can be done in Fiji also using the magic wand. And what we do is take the area of the inside of this yellow line, save this region of interest, and what we'll do is compile that into the Simpson's rule formula spreadsheet where we'll determine the volumes of this region. And what I just showed you is the binary image of this image, which is used in the voxel counter method to determine volumes. And again, just to reiterate, this ellipsoid method is not applicable to a structure like this, the whole brain or weirdly shaped structures within the brain. Is just not going to cut it. So we can take these volume calculations a step further and provide really, really neat visualizations for the volume calculations that we calculate. And so what we'll do is during the sectioning process of the tissue, we'll actually take images of the block face every sixth section, and we'll compile these images into an image stack and through some processing steps, create a 3D reconstruction from that image set. And so we found that every sixth section is a really good frequency for getting a nice, smooth, detailed volume reconstruction. And this is true for large and small brains. We just finished reconstructing some rat brains, and we had about 95 images with this frequency every sixth section through the sectioning process. And it came out really, really well. So the images are cropped and aligned in Fiji or in Photoshop, whatever software is best. Fiji works very nicely. Photoshop works very nicely. I tend to use Fiji because I use it for most everything else. So with these image stacks, we can create volumes, but also surface maps. So the volumes will show tissue in any plane. So the tissue may have been sectioned in the coronal plane, but once we have these images combined, you can actually go through and see the brain sectioned sagittally, horizontally, and even oblique sections. So you can go in at really any angle that you'd like and take a peek inside. Now, the surface map offers another benefit in that if you wanted to see secondary structures within the entire brain, this would be a very useful application for doing so. And we'll get to some examples here in a second. And taking a step further, we can actually take stained tissue and using linear, nonlinear transformations in Fiji, we can match those stained tissue sections to the block face images using those as a template and create a stained 3D reconstruction of the tissue. Now, granted, this does require a very high frequency of stained slides to reveal a good reconstruction. So staining every 24th section or even every 12th section it might not give you a very, very good reconstruction. So the frequency has to be even higher before you can get a good stained tissue reconstruction. So let's look at some examples. We have a grizzly bear reconstruction as well as a pig brain reconstruction that we've been working with recently. And I am very excited to show you guys. So we'll start off with the grizzly bear brain, and I've already loaded these into Fiji, done the processing. So what I'm going to show you first actually is the block face stack. This is rather small. Let me blow this up a little bit for you guys. So these are the block face images taken while the tissue is being sectioned. And this stack has actually not been aligned. You can see it bouncing around a little bit. So this is a pre-aligned block, but just to give you an idea of the images that are taken through the sectioning process. So this goes throughout the entire grizzly bear brain coronally. And we actually started in the caudal end and cerebellum. So this is going towards the olfactory tubercles here. So what we do with these images is load them up into Fiji, perform all the processing steps, and then what we end up with is something that looks a little like this. Now it still has some artifact down here which can be cleaned up. So this is the grizzly bear brain right here. For some reason, it's not letting me rotate. I'm not sure why, but this in the 3D viewer in Fiji, this is actually able to be rotated. I'm not sure why it's not letting me do so at the moment. Let's see. Maybe if I try. Let's try opening it again. So when you first upload it, it's got this nice, beautiful white block, so you can't see anything. So we've got to get rid of that. And so all that requires is a simple transfer function, alpha transfer function adjustment. And here we go. There we go. So in this 3D viewer, we can rotate this any which way we want to. So this is the reconstructed grizzly bear brain. As you can see, it's got quite the olfactory bulb up there. And what I also did, and we'll see if I have to upload this one again. There's another feature in Fiji that we use. It's called Volume Viewer, and this actually allows you to section through at any plane and view it in any plane. The processing speed is a little bit slower in this, so as you can see by the pixelation here. But what we can do, so this was sectioned coronally. So when we look at it coronally, I'll let that depixelate there. So we section coronally and we get these nice images here. Now, since we made a 3D volume reconstruction, we can go into the sagittal plane and also zoom through the brain. So this is going through the grizzly brain in a sagittal plane. And because the number of images that were taken of the block face, we're getting a nice smooth reconstruction throughout, even though it wasn't sectioned in the sagittal plane. And we can also go through horizontally. I know the pixelation can kind of be annoying. It takes it a second to readjust itself, but once it does, the images are definitely well worth viewing. So this is just another handy tool that we have and utilize when we are working with the blackface reconstructions. So what I also put together is a stain set of the grizzly bear brain. So we stained with a Nissl thionin stain, and we also stained with a wild myelin stain. And the next volume that I'm going to show you is actually of the myelin stained slide set. And so we used linear and nonlinear transformations to match these slides with the block face images, and it actually comes out to be a nice reconstruction. You can see the white matter stained here in a dark purple, while the gray matter is the nice brown tan color. And so just like we did with the block face images, we can upload this as well into Volume Viewer. And I actually just want to show one more thing before we move to that. Because there's a difference in color in this between the white matter and the gray matter, we can actually take away some of this gray matter and left with some of the white matter tracks in the brain. This one's not showing it as well as I'd like. Let's go ahead and load it up into the Volume Viewer. So just like the block face images, we get a view over here of the coronal plane, sagittal, and horizontal. And just like the block face, we can go in coronally. This is the plane that it was sectioned in. You will notice a difference in staining intensity. I performed an intensity normalization across the stack, and it did a pretty good job. But as you can see over here, there's still a few differences in intensity. Not so much that it's taking away from the myelin stain. So now we go into the sagittal plane. And again, we get a pretty good stain set reconstruction even in the sagittal plane here. It's pretty smooth given the number of slides that were used to recreate it. And lastly, we go through the horizontal plane. Now, if we take this image right here and rotate it, we get an oblique cut through the brain. And some of these views may be more helpful for viewing certain structures than coronal, sagittal, or horizontal might show you. Okay. So now let's go into, let's see, I've got a pig brain here for you. All right. Let's open up the pig brain here. So again, this was taken from Blackface Images. And I've also included thionin sections in here, but I went ahead and added a Gaussian blur to the stack, so it will be more smooth for the reconstruction. As I go through here, you can probably catch a few glimpses of the blue staining, especially back towards the end when cerebellum comes into view. So you can kind of make out a little blue tincture here. And again, back here in cerebellum. So let's see what this looks like in the 3D viewer. So we get a nice volume reconstruction here with the Blackface image combined with the thionin set. Gives you nice detail, nice smooth surface. And just like with the others, you can upload this to Volume Viewer and look at it in a number of different planes. Very, very pixelated here. See if we can go through here. So again, this is just showing an oblique cut through the pig brain. If we wanted to go into the coronal, we could do that. Again, sagittal, finally horizontal. So in addition to Fiji, as being an open source form of volume rendering, there's also another called Slicer that I'll show you here. And these open source software packages are really, really a good source to just download, play around with. They're very valuable, and as you can see, they have really good algorithms incorporated into the software that can create very good volume rendering, really good analysis tools. So let's upload that same, actually a grayscale version of this. So we've got a few adjustments to make before this looks like a brain. It's kind of squished right now. So let's change this. All right, so we are now ready to render this. And here we go. So this is a little bit darker than what it needs to be, so make a few adjustments here. So this is also one of the software packages that we use for volume rendering and volume adjustments, thresholding, just lots of different options for this. So the other neat thing about this package, I'll show you here. So you have these ROIs, these little colored balls on the side of each face of the cube here. And what we can do is take these, drag them any which way you want, well, in a vertical or horizontal or coronal, sagittal, or horizontal plane. And then you can block off the tissue and look at specific areas instead of looking at, slice by slice. So just another tool to consider with this package. So that pretty much covers the volume reconstructions. Now I'm going to go into more of the surface map, and this offers a pretty interesting benefit, and this is also part of our website. We have a 3D reconstruction services page that we just recently added. So this is a surface map of that same pig brain. And this is completely interactive. I encourage you to go to our website, play around with it, explore it. So with the surface map, you're not getting the information on the inside. As you can see, it's a shell of the tissue. But what makes this interesting is that if you have subcortical structures that you've also made reconstructions of, you can view these within this shell. You can change the transparency of this so that you're able to see different structures within the shell of the entire brain. And I'm going to take you to another example to show you this. And again, open source software programs, Mesh Lab is a great one. So what we would do is take the surface map information from Fiji here and export it, and then upload it into Mesh Lab here. So what we did was, if you remember the grizzly brain from earlier, we took a section through that, made a reconstruction here. But what we also did is create a reconstruction for a structure that is found right through here bilaterally, called the claustrum. So I'm going to turn this on. You can't see it now, but what we can do, since this is a surface map, so we can actually go inside this slab of tissue. And so this is the colostrum right here, the reconstructed colostrum. And we can change the viewing options here since it is made out of a mesh. So you can rotate this and view the structure from any vantage point. So this is another very handy software package, which is, as I mentioned before, open source and very, very handy. And you can also view the structure by itself if you wanted to. Okay, so I'm going to show you one more software program that we use for showing surface maps. So this is called ParaView, and this actually gives you a more detailed look at the subcortical structure versus the entire brain than does MeshLab. So in MeshLab, you kind of get lost in what you're looking at, whether it's the entire brain or the structure within that brain. So what we can do here, I've already changed the transparency here. Let me turn this back to 1. So what we have here is that same slab. We change the opacity, and right now there's nothing there. It's an empty shell of a brain. But I've got the colostrum uploaded up here. So now you can see the structure even better. And again, if you wanted to look at one versus the other, you can do that as well. All right, let's go back to the PowerPoint here. So that basically covers the 3D reconstructions, volumes and surface maps. So the more images you have, the better reconstruction you're going to have, and that we can produce. And so, like I said, we found that every 6th section gets a very good number of images, both large and small brains, to view. And like I said earlier, this isn't, I know I showed you larger brains, but we also perform 3D reconstruction volumes and surface maps for mice and rats. And some actually just finished up with a few rat brains a few days ago that came out quite nicely and had about 95 images, which was every 6th section through the block. So that's going to wrap it up for this webinar today. I just want to remind you of some of the benefits of choosing NSA for both your neurohistology and imaging and analysis needs. So when you choose NSA for your neurohistology, you're getting the highest quality and most efficient neurohistology, and then you can combine that with the high quality imaging and analysis processes that we also offer. And the good thing about that is that you're not having to send your tissue or your slides to multiple locations. We can do all of these things in one location and send them back to you without worrying about shipping to many other locations. So one other thing I wanted to mention is that we have a color calibration system that we use for imaging and image analysis. When we perform the image analysis, we perform a white balance correction as well as a color calibration so that all of the images are going to be the same. So you're not getting any variation within the analysis project. All of those images are going to have the same color throughout. And I also wanted to mention that each analysis project is very unique. There's different challenges presented by each and every one. So whenever we are looking at a project, we always look at it from many different angles, try to determine the best and most efficient way to get the data that you need for your study. And it's the highest quality with the color calibration, and on top of the best neurohistology that you can find around. So with that, I will bid you guys adieu. And if you have any questions, please email us at info@nsalabs.com or give us a call at 865-675-2245. Thanks for joining us today. We really appreciate it. Have a good